Hello, welcome back. We have been talking about randomized primality testing using Fermat-Euler theorem. We are trying to answer this question: what is the probability that a composite number is wrongly declared as a prime by this algorithm? For that, I have been building up on some basic mathematical theorems on subgroups. Today, I will talk about one more theorem that we will need to answer that question. Okay, let's get started with the theorem. So the theorem is as follows. It's a very interesting theorem. Suppose you have a finite group and let's assume H is a subset of G. Even more, H is a subgroup of G. Okay, and it's a strict subgroup. Okay, what it means, strict subgroup, is that there are elements outside H. Okay, meaning not all elements of G are in H. Basically, there are some elements outside here. Okay, so we have the group G, the big group, and the subgroup H. The theorem is all about what is the maximum size of the subgroup. Okay, the theorem is saying that the size of the group H, right, is bounded by half of the size of the group G. That's an interesting theorem. If you think about it, it is giving us an upper bound on how many elements can we expect to find in this subgroup H. Okay. Why is this interesting for us? It's going to be soon clear why we need this when I talk about the primality testing in the next segment. Okay. So for now, let's focus on how do we prove this fact that a subgroup cannot have more than half of the elements of the group that we are working with, the group G. Okay. How do we prove this? So the way I'm going to prove is as follows. I'm going to select an element that's outside the subgroup H, which must exist because we said H is a strict subgroup of G. That means there must be an element that we can take outside H. Let's call it H bar. Okay. So H bar is an element outside the subgroup H. Okay. Now we take H bar and multiply with each element of H. So we take this and multiply it with this. We take this, multiply with this, H bar. So all of the elements of H are multiplied with H bar. Okay, that means we are generating another set. Okay, so let me write it formally here. H bar, the capital H bar, is a new set that we are going to form by taking all the elements of H, right, and multiply it with H bar. So algebraically, H bar is obtained by taking all elements from group H and multiplying it, or take H bar and multiply with every element of the group H. So this is basically how we formed H bar. Okay, so now we need to prove two things. We need to show H bar and H are two disjoint sets, meaning there are no overlaps between these two sets, and they are of equal size. So I'm going to prove, in order to prove that H is bounded by G by 2, I'm going to prove this. I'm going to prove first that H intersection of H bar is empty. This is one fact I need to prove. Okay, I'll prove the second. This is the second fact. Okay, this is the empty set. I need to prove that. And the very first fact that I need to prove is that the number of elements in H is same as the number of elements in H bar. Okay, so I need to show to you H is equal to H bar in terms of the size. Okay, so if we are able to somehow prove this, then we can immediately conclude that the size of the set H is bounded by G by 2. The reason is as follows. Suppose, let's assume somehow magically we prove these two. Okay, what can we say about the total size of H and H bar? Since they are equal, it's same as 2 times H. Okay, but G is a bigger set where H and H bar are subsets. Okay, so in order to compute the size of G, we will be computing the size of H bar, and there are no overlaps. Okay, therefore, if we add them, the size of G must be at least 2 times the size of H. Okay, that means H is bounded by G by 2. That's basically the argument. Let's first consider the first fact. We need to prove that the subgroup H has same number of elements as the subset H bar. Okay, how do I do that? So I'm going to first show this way that, by the way, we know H is a finite subgroup and H bar is also a finite subset. Therefore, we can easily now prove that they both are equal length as follows. Let's assume there is some collusion, meaning we took, say, H1 and H2 from the subgroup H, right? And we multiply it with H bar, and they collided, meaning H bar times H1 is equal to H bar times H2. Okay, let's assume like this. Where is H bar coming from? H bar is a group element G, therefore we can invert and cancel out H bar on both sides. So H bar will cancel out. So we will show that H1 is equal to H2. Okay, that means the elements of the group, or rather the elements of the subset H bar are all distinct. Okay, that's what we have shown just now. There are no duplicates in this subset H bar. Okay, all right, which means that they must be of equal length. The number of elements in H must be equal to the number of elements in H bar. Okay, because we are talking about two sets. Okay, and they both are, we establish a one-to-one mapping essentially. That means two finite sets with one-to-one mapping means they must be of equal length. That's the reason why we claim that both H and H bar are of equal lengths. Okay, so let me refresh the proof one more time. We selected two elements H1 and H2 in H. In case there is a collusion inside a H bar, what it means is that H bar times H1 is same as H bar times H2, right? That means we can cancel out H bar on both sides. We get H1 equal to H2. That means we establish a one-to-one mapping between the set H and the set H bar. Therefore, since they are finite, therefore they must be of equal length. Right, let's prove the second part of the theorem, that there is no overlap between the set H and H bar. So in order to prove that, we will use proof by contradiction technique. That means we assume there is an overlap between H and H bar. What it means, H and H bar to have overlap, let's assume there exists some element H, okay, in the set H, and of course assume that H comma or H bar times H is also in H bar, okay, and in H. So that's the meaning of overlap, right? So we found an element which is present in both H and H bar. Okay, so now we will make use of this and prove by contradiction that H and H bar should not have any overlap. Okay, let's think about it. We know that H bar H is belonging to H for some H. Okay, let me call that H bar H as H prime. Okay, just to make the notation easier, equal to H prime. And of course, since the left-hand side is part of the H, the right-hand side H bar must also be part of H. This implies H bar is an element in H prime rather is an element in H. Okay, and what are we going to do next? We will take multiplicative inverse of H on both sides, which exists because we are working with H being the subgroup. We can do multiplicative inverse easily, which means H bar is nothing but H inverse times H prime. Okay, all right. Now we will use a theorem that we proved earlier. So remember, H is an element in H, and H inverse is of course an element in H. Okay, we also learned that H prime is also an element in H. Okay, what can we say? That means the property of closeness is telling us that the product must also be an element in the subgroup H. Okay, so H inverse is an element in H. H prime is also an element in H. Therefore, H bar is an element in H, which is a contradiction because H bar is a part of H bar only, not part of H. Okay. So let me quickly summarize the proof. We wanted to show that there is no overlap between these two sets. Okay. The method of proof by contradiction means we assume the opposite. Let's assume there is an element that is present in both H and H bar. So for some H element in the set H, we argue that H bar times H is present in H bar and also in H. Okay, this is basically the proof of contradiction technique that we're starting now. Okay, and I'm going to call h bar h as just h prime. Since this is an element in h prime is also an element in h. Okay, and I'm going to take multiplicative inverse on both sides by canceling out h. So I get h bar is h inverse times h prime. Okay, since h is an element in h and h is a subgroup, h inverse must exist and it's also part of h. Okay, so this part is part of h and h prime is also part of h. We established here. Therefore, because h is a subgroup, when you multiply two elements, the answer is also part of the subgroup. Okay, on the left hand side we have h bar. That means h bar is also part of h, which is a contradiction because h bar is an element not supposed to be in h. It's part of outside the h. That's how we started the theorem. Okay, h bar is an element not in h. Okay, so we proved that this fact is also true. Okay, now we don't need to prove the major theorem that the number of elements in the subgroup is bounded by g by 2. Now how do we prove that? So in order to compute the number of elements in this group, we need to compute number of elements in disjoint sets. Okay, and what are the disjoint sets we have? We have two sets at least, h and h prime, h and h bar rather. There may be more disjoint sets, but we don't care. So we do know that the number of elements in G must be at least the number of elements in H and the number of elements in H bar. But we proved that H bar has same elements as H, therefore same number of elements as H. Therefore, I can just write it as 2 times H. Okay, which means we can just write it in the reverse. The number of elements in H is bounded by basically dividing it by 2 on both sides and rewriting the H and G is nothing but G by 2. Okay, so this is a very interesting theorem that tells us how many elements can we expect, how many maximum number of elements can we expect within a subgroup. Okay, so to give you a concrete example, suppose you take say Z star 11. Okay, Z star 11 means a group containing all the elements from 1 through 10, inclusive of 10. So I can give you a subgroup, for example, a mod 11. The answer is part of this. For example, take 3 into 4, multiply it, you get 12. 12 mod 11 is 1, you get 1 here. Multiply 3 into 5, 15. 15 mod 11 is 4, you get 4 here. Find 9, 45 mod 11, you get 1. So you can check for yourself that it is closed, associative, multiplicative inverse exists. For example, 4, if you multiply 4 with 3, you get 1. That means the multiplicative inverse of 4 is 3. What about for 5? For 5, if you multiply it with 9, you get the inverse. The inverse of 5 is 9. Okay, so you can check for yourself that this is a subgroup and the number of elements is only 5. You cannot find anything more than 5 for this Z star 11. Okay, that's basically because of the theorem we just proved. Okay, that's all. Thank you very much.